Welcome back, Night Traveller. Tonight, we're drifting into the story of rogue planets, worlds that wander the galaxy without a sun to call home, moving through darkness so complete it defies imagination. If you're finding comfort in these cosmic tales, a gentle like or subscription helps more people discover this quiet corner of the universe. And if there's a topic calling to you, some corner of science or space that pulls at your curiosity, leave it in the comments below. Your suggestions shape these journeys. Now let's begin. There's something almost mythological about the idea, isn't there? A planet spinning silently through space with no star to orbit, no sun rising on its horizon, no warmth cascading across its surface at dawn, just darkness, endless, absolute darkness. These are rogue planets, worlds that drift through the galaxy completely alone, untethered from any solar system. They don't circle a parent star like Earth circles the Sun. They simply move, carried by momentum from some ancient catastrophe, gliding through the void between stars like ships without harbours. Imagine standing on the surface of such a world. Above you, no sun. Around you, no neighbouring planets catching starlight. Just the faint, impossibly distant glow of stars scattered across the black. It would be the loneliest vista in the universe, a planet experiencing eternal night, where every moment is midnight, and midnight stretches backward and forward through all of time. And yet, these worlds exist. Not as rare anomalies, but perhaps as one of the most common types of planets in the galaxy. They're out there right now, billions of them, wandering in silence through the dark spaces between the stars, worlds without suns, planets that never knew what it meant to bask in light. But rogue planets weren't always alone. Most of them began their existence much like Earth did, forming in the swirling disk of gas and dust around a young star, coalescing from the same cosmic material that would eventually build entire solar systems. So, what happened? How does a planet go from orbiting peacefully around a star to being flung into the endless dark? The answer lies in the chaos of planetary formation. When solar systems are young, just a few million years old, they're violent, unstable places. Planets are still finding their orbits, still jostling for position in the gravitational dance around their star. And sometimes, in these early days, our planets get too close to one another. Picture it. Two worlds, perhaps one the size of Earth and another the size of Jupiter, their orbits slowly intersecting over millennia. Eventually they pass close enough that their gravity begins to pull at each other. Not gently, but with enough force to alter their paths. The smaller planet might get yanked inward, spiralling toward the star, or it might get flung outward, its velocity increasing until it's moving too fast to stay bound to the solar system at all. And just like that, it's ejected, cast out, sent tumbling into interstellar space at tens or hundreds of kilometers per second, never to return. The orphan of planetary formation, banished by the very gravitational forces that created it in the first place. A world that once knew the warmth of a nearby star, they're now condemned to wander the galaxy in solitude for billions of years. Here's where the story becomes almost overwhelming in scale. Scientists estimate, based on gravitational microlensing observations and statistical models of planetary formation, that there could be billions of rogue planets in the Milky Way galaxy alone, perhaps even trillions. Let that settle in for a moment. Trillions. Our galaxy contains somewhere between 100 and 400 billion stars. That's already a number difficult to grasp. But if current estimates are correct, rogue planets might actually outnumber stars. For every sun you see twinkling in the night sky, there could be 2, 3, maybe even 10 dark planets drifting unseen in the spaces between. They're everywhere and yet nowhere, invisible, silent, each one following its own unique trajectory through the galaxy, influenced by the gravitational pull of passing stars but never captured, never slowing down enough to settle into orbit again. It changes the way you think about the galaxy, doesn't it? We imagine space as mostly empty, vast voids punctuated by the occasional star or planet. But if rogue planets are as common as the data suggests, then the galaxy is far more crowded than it appears, not with light, but with worlds. Dark worlds. Worlds we'll likely never see, wandering through the cosmic night just beyond the reach of our telescopes. The Milky Way isn't just a collection of solar systems, it's a sea of wanderers. Finding a rogue planet is almost absurdly difficult. Think about it. These worlds emit almost no light of their own. They don't reflect starlight the way planets in solar systems do. Because there's no nearby star to illuminate them. They're cold, dark and small compared to stars. It's like trying to spot a single black pebble in a vast unlit cavern. The first candidates for rogue planets were discovered in the 1990s, but confirmation took years, decades in some cases. Astronomers had to develop entirely new techniques just to glimpse these invisible wanderers, and even now, with advanced telescopes and detection methods, we've only confirmed a handful of rogue planets with certainty. Most of what we know comes from statistical inference, looking at how often certain gravitational events occur and extrapolating backward to estimate how many dark planets must be out there to produce those observations. It's humbling in a way. We've mapped the surfaces of distant moons, has analysed the atmospheres of exoplanets hundreds of light years away, and photographed galaxies billions of light years distant. But these planets, some of which might be closer to us than the nearest star, remain almost completely hidden. Shadows in the dark, ghosts in the cosmic machine, and yet slowly we're learning to see them, not with visible light, but through the subtle bending of space-time itself. The technique astronomers use to find rogue planets is called gravitational microlensing, and it's one of the most elegant pieces of observational science ever devised. Here's how it works. Imagine a rogue planet drifting through space, passing between Earth and a distant star. The planet itself is invisible, too dark and too far away for our telescopes to detect directly. But even though we can't see the planet, we can see what it does to space-time. According to Einstein's general relativity, mass warps the fabric of space-time, and when light from that distant background star passes near the rogue planet, it follows the curves in space-time created by the planet's gravity. The light bends, just slightly, around the planet. From our perspective on Earth, this bending causes the background star to briefly appear brighter, sometimes twice as bright, sometimes even more, for a few hours or days as the rogue planet passes in front of it. Then, as the planet continues on its journey, the star returns to its normal brightness. The event is fleeting, unrepeatable, and often lasts only as long as it takes the planet to cross our line of sight. It's a bit magical when you think about it. The universe itself becomes a telescope, gravity becomes a lens, and for just a brief moment, the invisible becomes visible, not through light, but through the curvature of space and time. Each micro-lensing event is a whisper from the dark, a rogue planet announcing its existence, not with light, but with gravity's gentle signature. Without a star to warm them, rogue planets exist in a kind of cold that's difficult to truly comprehend. Most of them have surface temperatures hovering just above absolute zero, around negative 270 degrees Celsius or negative 450 degrees Fahrenheit. Absolute zero is the point where molecular motion nearly stops, where heat, as we understand it, ceases to exist. It's the coldest possible temperature in the universe, the bottom of the thermodynamic scale. And rogue planets live just barely above that threshold, their surfaces frozen solid, or their atmospheres, if they have any, collapsed into frost and ice. But here's where the story takes an interesting turn, because while the surfaces of these worlds are frozen beyond anything we experience on Earth, their interiors might be surprisingly warm. Deep inside a rogue planet, radioactive elements decay slowly, releasing heat. It's the same process that keeps Earth's core molten, that drives our volcanoes and tectonic plates. And on a large enough rogue planet, this internal heat could persist for billions of years, long after the planet was ejected from its solar system, long after its surface froze solid. So picture it, a world encased in ice kilometers thick, the surface temperature cold enough to freeze air itself. But beneath that frozen shell, a warm core, perhaps even liquid water, heated by radioactive decay and insulated by layers of rock and ice, an island of warmth buried inside a frozen fortress, drifting through the cosmic dark. It's a strange inversion, isn't it? We think of warmth as coming from above, from the sun, from fire, from light. But on a rogue planet, warmth comes from within, from the slow, patient decay of atoms that have been releasing heat since the planet formed billions of years ago. For most of human history, rogue planets were invisible to us. Not just difficult to see, truly invisible. We had no way to detect them, no technology capable of glimpsing these dark wanderers. But gravitational microlensing changed everything. Suddenly, the universe gave us a tool to see the unseeable. When a rogue planet passes between us and a distant star, that star brightens briefly, just for a few hours or days, as the planet's gravity bends and magnifies the starlight. It's an extraordinarily rare event. The alignment has to be nearly perfect. The rogue planet has to cross almost exactly between Earth and the background star, and we have to be watching that particular star at that particular moment. Miss the window, and the planet vanishes back into invisibility, its presence unrecorded. That's why finding rogue planets requires monitoring millions of stars simultaneously, waiting patiently for one of them to brighten in just the right way. Astronomers use automated telescopes that photograph the same patches of sky over and over, night after night, comparing each image to the ones before, searching for that telltale temporary brightening. And when they find it, when a star's light curves in exactly the pattern predicted by a planet-sized mass passing in front, it's a moment of quiet triumph. Because for just a brief instant, the universe revealed something it usually keeps hidden. A world that exists in darkness became visible, not through its own light, but through the way it bent the light of stars behind it. The universe itself became our telescope, gravity our lens, and space-time our guide. The smallest confirmed rogue planets are roughly the mass of Mars, small rocky worlds ejected from their solar systems in the chaos of planetary formation. But the largest rogue planets are strange, enormous things that blur the line between planet and star. These massive rogues can be many times the mass of Jupiter, the largest planet in our solar system, and at some point, SEMS. As you add more and more mass to a planet, something interesting happens. It starts to resemble a brown dwarf. Brown dwarfs are sometimes called failed stars, objects too massive to be planets, but not quite massive enough to ignite the hydrogen fusion that powers true stars. They exist in a kind of twilight zone between planetary and stellar, neither one nor the other, and the largest rogue planets occupy that same ambiguous space. Some of them might have formed like planets, coalescing from the disk around a young star before being ejected. Others might have formed in isolation, collapsing directly from a cloud of gas and dust without ever belonging to a solar system. So the question becomes almost philosophical. What makes a planet a planet? Is it the way it formed? The fact that it orbits a star, its mass and composition? Or something else entirely? The International Astronomical Union, the organisation that famously downgraded Pluto, has struggled with this question. Their definition of a planet requires that it orbit a star, which would technically exclude rogue planets altogether. But that feels unsatisfying, doesn't it? These are worlds. They have mass, gravity, possibly atmospheres and moons. They're planet-like in every way except their orbit. Maybe the universe doesn't fit neatly into our categories. Maybe there's a spectrum of objects, from small rocky worlds to massive brown dwarfs, and rogue planets exist somewhere along that continuum, defying our attempts to classify them cleanly. Perhaps the cosmos is content being undecided. Most rogue planets were ejected from solar systems, cast out by gravitational chaos, sent tumbling into interstellar space. But some rogue planets never belong to a solar system at all. These are worlds born in isolation, formed not from the disk around a young star but from collapsing clouds of gas and dust in the depths of space. Regions where the gas was just dense enough to collapse under its own gravity, but not dense enough to ignite fusion and become a star. Instead, the cloud collapsed into a planet, a world that never knew a sun, that never orbited anything, that formed alone in the dark and has been drifting through the galaxy ever since. It's a lonely origin story, isn't it? We think of planets as being born alongside stars, as children of solar systems, shaped by the light and heat of their parent suns. But these isolated birth rogues challenge that narrative. They're planets that exist outside the usual story of planetary formation, worlds that came into being in the cold, empty spaces between stars, and they've been drifting ever since, through darkness that predates their existence and will outlast their eventual cooling. Planets born into night, destined to wander it forever. If a rogue planet has an atmosphere, and some of them surely do, it would be a strange, still place. No winds howling across the surface, no storms rolling through distant hemispheres, no weather patterns sweeping from equator to pole. Because weather as we know it is driven by energy from the sun. Solar radiation heats the atmosphere unevenly, creating temperature differences that drive air currents, winds, storms. On Earth, the sun's warmth creates the complex dance of high and low pressure systems, the jet streams, the hurricanes and monsoons. But on a rogue planet, there's no sun to drive that process. The atmosphere, if it hasn't collapsed entirely into frost on the surface, would be in a state of near-perfect stillness, a frozen equilibrium. Any clouds that formed billions of years ago, when the planet still had internal heat escaping into its atmosphere, might still be hanging there, motionless, preserved like fossils in the sky. Imagine it. Clouds that haven't moved in 100 million years, an atmosphere locked in stasis, unchanging, the same patterns visible overhead for epochs, a sky frozen in time. It's the kind of stillness that doesn't exist anywhere on Earth. Even our quietest places have wind, have weather, have change. But on a rogue planet, the atmosphere would be a monument to stillness, a reminder that without a star's energy, motion itself becomes rare. Just silence, just stillness. Just the slow, patient cooling of a world that time has almost forgotten. In 2011, a team of astronomers published findings that fundamentally changed how we think about the galaxy. Using microlensing data from years of observations, they estimated that Jupiter-sized rogue planets might be as common as main sequence stars, the ordinary hydrogen-burning stars like our Sun that populate the Milky Way. Let that thought settle for a moment. As common as stars, we've always imagined the galaxy as a collection of solar systems, stars with their attendant planets, moons and asteroids, all bound together by gravity. And in between these solar systems we imagine mostly emptiness, vast stretches of space where nothing much exists except the occasional hydrogen atom and faint wisps of interstellar gas. No, but this discovery suggested something different. The galaxy isn't just stars and their planets. It's also populated, perhaps equally populated, by dark worlds wandering between the stars. Planets that don't show up in our telescopes, that don't appear on any map, but are there nonetheless, drifting silently through the void. If you could somehow light up every rogue planet in the Milky Way, the galaxy would look completely different. Not just stars scattered across the darkness, but planets too. Billions upon billions of them, filling the spaces between solar systems with invisible worlds. It's a humbling realization. We thought we understood the galaxy's population. We'd counted the stars, mapped the nebulae, catalogued the star clusters. But we'd missed half the population, or more, because we were only looking for things that shine. The dark matters just as much as the light, and the galaxy is far more crowded than we ever imagined. When a planet forms, the process is violent, material crashing together, potential energy converting into heat, the young world glowing from the warmth of its own assembly. In those early days, even worlds far from their parent stars can be scorching hot, heated not by sunlight, but by the energy of their own formation. And that heat doesn't disappear quickly, not on geological timescales anyway. A massive planet, something Jupiter-sized or larger, retains the heat from its formation for billions of years. It cools slowly, radiating warmth into space at a rate so gradual that even after eons, its core remains hot. Not star-hot, but warm enough to drive geological processes, warm enough to keep its interior molten. Rogue planets are like cosmic embers. They were born in fire, in the chaotic heat of planetary formation, and they've been cooling ever since. But the cooling is so slow that even now, billions of years after ejection, some of them are still warm inside. It's a strange kind of heat, isn't it? Not the warmth of sunlight cascading across a surface, but the deep, internal warmth of a world remembering its own birth. Heat escaping from the core, rising through layers of rock and metal, perhaps reaching the base of a frozen ocean buried beneath kilometers of ice. On the largest rogue planets, this internal warmth could sustain geological activity for longer than our solar system has existed. Volcanoes might still erupt on the seafloor of a subsurface ocean, heated by the planet's slow cooling. tectonic plates might still shift as are driven by convection currents in the mantle. All of this happening in complete darkness on a world that hasn't seen starlight in billions of years. An ember glowing faintly in the cosmic night, too dim for us to see, but glowing nonetheless. Here's an unsettling thought. A rogue planet might have already passed through our solar system, and we would never have known. If it happened thousands of years ago, or even hundreds, before we had telescopes, before we understood orbital mechanics, before we were even paying attention to the sky in a systematic way, there would be no record of it. Just the invisible hand of a wandering world reaching through our cosmic neighborhood, tugging gently on the orbits of distant planets, and then continuing on its way. The effects might have been subtle, a slight change in Neptune's orbit, a minor perturbation in the asteroid belt. Nothing catastrophic, nothing immediately obvious, but enough to leave a fingerprint in the gravitational dynamics of the solar system, a fingerprint we wouldn't recognize even if we were looking for it, and the rogue planet itself. It would have passed through and moved on, already light years away by the time we developed the technology to detect such things. A visitor in the night, unobserved and unrecorded. The thought is both eerie and humbling. Our solar system feels stable, predictable, mapped. We know the orbits of the planets to extraordinary precision. We can calculate where they'll be centuries from now. But that stability might be more recent than we think. The solar system might have experienced close encounters with wandering worlds in the past, events that went completely unnoticed because humanity wasn't yet watching the skies. Space is deep and old, and in that depth, in that age, many things might have happened that left no trace in human memory, only in the subtle mathematics of orbits, waiting for someone clever enough to notice. One of the most intriguing possibilities about rogue planets is this. Some of them might have subsurface oceans. It sounds contradictory at first. How could a world in eternal darkness, with surface temperatures near absolute zero, possibly maintain liquid water? But the answer lies in that internal heat we talked about earlier, the warmth generated by radioactive decay deep in the planet's core. On a large enough rogue planet, that heat could be substantial. It would rise through the mantle, warming the layers above until eventually it reached the base of a thick ice shell covering the surface. And there, at the boundary between ice and rock, the temperature might be just right for liquid water. This isn't just speculation. We see the same phenomenon on some of the moons in our own solar system. Europa, one of Jupiter's moons, has a subsurface ocean beneath an icy crust. So does Enceladus, a moon of Saturn. Both are kept warm not by the sun, but by tidal heating, the gravitational kneading they experience from their parent planets. Rogue planets wouldn't have tidal heating, but they would have radioactive decay. And on the largest rogues, that might be enough to maintain oceans for billions of years. Picture it. A frozen surface, silent and still, with temperatures so low that even nitrogen freezes solid. But beneath the ice, kilometers down, liquid water. Perhaps even warm water near volcanic vents on the ocean floor, where heat from the planet's interior escapes into the sea. And in that darkness, in those subsurface oceans that have never seen light, could there be life? Life that evolved without photosynthesis, without sunlight, feeding instead on chemical energy from hydrothermal vents. Life that thrives in eternal darkness, in a warm ocean buried beneath a frozen shell, on a planet wandering the galaxy alone. It's one of the most profound questions raised by rogue planets. Does life need a sun? Or does it just need warmth, liquid water, and the right chemistry? We're standing at the edge of a revolution in rogue planet astronomy. The Nancy Grace Roman Space Telescope, or scheduled to launch in the mid-2020s, is expected to discover thousands of rogue planets. More than all previous observations combined, Roman is uniquely suited for this task. It's designed specifically for gravitational microlensing surveys, with a wide field of view and the sensitivity to detect even small planets passing between us and distant stars. Where previous missions might have found a handful of rogue planets, Roman could find hundreds or thousands, and with that flood of data will come answers to questions we've been asking for decades. How common are rogue planets really? What's their size distribution? Are most of them rocky worlds like Mars or gas giants like Jupiter? How many were ejected from solar systems versus born in isolation? Do they have moons, atmospheres, subsurface oceans? Right now, rogue planets are rare curiosities. We know they exist, but our sample size is tiny. Just a few confirmed examples and a handful of candidates. We're making educated guesses based on limited data, trying to understand an entire population of worlds from just a few glimpses. But Roman will change that. It will transform rogue planets from a theoretical oddity into a well-studied class of objects. We'll go from knowing almost nothing to having statistical distributions, population models, formation theories backed by actual observations. The galaxy is about to reveal one of its best-kept secrets, and we're going to be here to witness it. This quiet revolution happening in the dark spaces between stars as we finally learn to see the invisible wanderers that have been there all along. Even in a galaxy containing hundreds of billions of stars and possibly trillions of planets, rogue planets travel through voids of almost incomprehensible emptiness. Consider the distances involved. The nearest star to our Sun is Proxima Centauri, about 4.2 light-years away. That's roughly 40 trillion kilometers. It's a distance so vast that light itself, travelling at 300,000 kilometers per second, takes more than 4 years to cross it. Now imagine you're on a rogue planet drifting through interstellar space. Your nearest neighbour, another rogue planet perhaps, or a distant star, is likely millions of kilometers away at minimum, more probably billions. The next closest object after that? Billions more. You could travel for millennia and never come particularly close to anything. No planets to see in your sky, no sun to warm your surface. Just stars scattered like distant pinpricks across the darkness, so far away they appear as nothing more than faint points of light. It's a loneliness that transcends anything we experience on Earth. Even the most remote places on our planet, the middle of the Pacific Ocean, the Antarctic Plateau, the depths of the Sahara, are teeming with life and activity compared to the isolation of a rogue planet. On Earth, you're surrounded by atmosphere, by electromagnetic radiation from the sun, by the gravity of the moon tugging at the oceans. You're embedded in a system connected to other bodies through forces and fields. But on a rogue planet, there's almost nothing. Just the faint gravitational pull of distant stars, so weak as to be nearly negligible, and the even fainter pressure of starlight. You're essentially alone in a way that's difficult to conceptualize, travelling through a galaxy that's simultaneously crowded with stars and emptier than any human experience. The journey of a rogue planet is the loneliest journey in the universe. Rogue planets move fast. Relative to the stars around them, they're travelling at speeds of tens to hundreds of kilometers per second. cosmic bullets racing through the galaxy. To put that in perspective, 100 kilometers per second is 360,000 kilometers per hour. At that speed, you could circle the Earth at the equator in about 7 minutes. You could reach the moon in just over an hour. And yet, despite these tremendous velocities, rogue planets give the impression of moving in slow motion. Because space is so vast, even travelling at 100 kilometers per second, it takes thousands of years for a rogue planet to cover the distance between stars. It's a strange paradox. Objectively, these worlds are moving faster than almost anything humans have ever built. Our fastest spacecraft, Voyager 1, is travelling at about 17 kilometers per second relative to the Sun. A typical rogue planet is moving 5 or 6 times faster than that. But from a cosmic perspective, they're creeping along, glacially slow. A rogue planet that passed near our solar system 1,000 years ago, around the time of the medieval period on Earth, is only now reaching a point a few light months away. Another few thousand years and it'll be a light year distant, then 2, then 10. Its journey plays out over timescales that make human history look like an eye blink. Geological eras pass, mountain ranges rise and erode. Entire species evolve and go extinct, and still the rogue planet continues, moving through the same patch of galaxy, its velocity unchanged, its trajectory almost perfectly straight, fast yet impossibly slow, urgent yet patient, racing through space at speeds we can barely imagine, yet taking millions of years to cross the galaxy. Time works differently when you're a wandering world. The term rogue planet is surprisingly modern. For most of human history, we didn't have a name for these objects because we didn't know they existed. The idea of a planet without a star was too strange, too outside our understanding of how the cosmos worked. But as astronomical observations improved in the late 20th century, and theoretical models of planetary formation grew more sophisticated, scientists began to suspect that ejected planets might be common, and so they needed a name. Some early astronomers called them nomad planets, which has a romantic, wandering quality to it. Nomads moving through the cosmic desert, following routes known only to themselves, unbounded by the gravity of any homeland. Others preferred free-floating planets, a more technical term that emphasizes their lack of orbital attachment. They float freely through the galaxy, unbound, independent, liberated from the gravitational constraints that hold other planets in place. And then there's rogue planets, the name that eventually stuck. Rogue carries connotations of rebellion, of breaking away from the norm. A rogue is someone or something that doesn't follow the rules, that exists outside the usual structures of society or nature. And each name captures something different about these worlds. The nomad emphasizes the journey. Free-floating emphasizes the physics. Rogue emphasizes the departure from the expected. But maybe the most poetic name would be the simplest, wanderers, because that's what they are in the end. Worlds that wander, planets without homes moving through the darkness, following paths written by ancient gravitational chaos, never stopping, never settling, never finding rest. Wanderers in the cosmic night. Young rogue planets, those ejected from their solar systems only a few million years ago, have a secret. They still glow, not in visible light. You wouldn't see them shining if you looked up at the night sky, but in infrared wavelengths they emit a faint warmth, a thermal signature from the heat of their formation that hasn't fully dissipated yet. This makes young rogues slightly easier to detect than their older cousins. Infrared telescopes can spot them directly, seeing their heat against the cold background of space. No need for microlensing, no need to wait for them to pass in front of a background star. They announce themselves through their warmth. But it doesn't last long, not on cosmic timescales anyway. After a few tens of millions of years, even the largest rogue planets cool enough that their infrared glow fades below detection limits. They become too cold to see directly, too dark to spot against the background radiation of space. And so they join the ranks of the truly invisible, the older rogues that have been wandering for billions of years, their formation heat long since radiated away into the void. But for that brief window, those first few million years after ejection, they carry the memory of their violent birth as a fading warmth. Like embers from a fire that's been extinguished, still glowing faintly in the darkness, growing dimmer with each passing year. Eventually the glow fades entirely, and the planet becomes just another invisible wanderer, indistinguishable from the billions of others drifting through the galaxy's dark spaces, the last light of their origin fading into the black. Here's a thought that borders on cosmic poetry. A rogue planet could theoretically be captured by a star's gravity and become a planet again. It's extraordinarily rare. The conditions have to be almost perfect. The rogue planet has to pass close enough to a star to fall within its gravitational influence, but not so close that it crashes into the star or gets flung away by a slingshot encounter. Its velocity has to be just right, slow enough to be captured, but fast enough that it doesn't spiral inward. And even if all those conditions are met, the resulting orbit would likely be highly elliptical and unstable, at least at first. Over millions of years, gravitational interactions with other planets in the system might circularize the orbit, might stabilize it. But the chances of this entire sequence playing out successfully are vanishingly small. Still, it's possible. Somewhere in the galaxy, at some point in its vast history, a rogue planet has probably been captured by a star. A wanderer finding a home after billions of years in the dark. Imagine that moment. If a moment can span millennia, a world that has known only darkness, and only the cold, empty spaces between stars gradually falling into orbit around a sun. The first light touching its frozen surface in eons, ice beginning to sublime, atmospheres stirring for the first time in ages. If there were anyone there to witness it, any hypothetical observers on that captured world, they would see something unprecedented in the universe, a sunrise after billions of years of night, the first dawn of a world reborn. It would be the ultimate redemption story, a planet given a second chance, a wanderer finally coming home. When we talk about planets being ejected from solar systems, it's easy to imagine some external catastrophe, a passing star perhaps, or a nearby supernova shaking things loose. But the truth is often more intimate, more tragic. Usually it's the other planets that do it. In young solar systems, our giant planets, worlds like Jupiter and Saturn in our own system, act as cosmic bouncers. Their immense gravity dominates the dynamics of the entire system. Smaller planets might form in stable orbits initially, but if they drift too close to one of these giants, the interaction can be catastrophic. Picture two planets approaching each other over thousands of orbital periods. Each pass brings them slightly closer, their mutual gravity tugging at their orbits, shifting their paths incrementally. Eventually they pass near enough that the gravitational exchange becomes violent. The smaller planet might be yanked inward, its orbit destabilized, sent careening toward the star, or, more commonly, it gets flung outward. The giant planet's gravity acts like a cosmic slingshot, accelerating the smaller world to escape velocity. One moment, it's a planet in orbit. The next, it's travelling too fast to remain bound to the system at all. And the giant planet, it barely notices. Its orbit shifts slightly. It might move a bit closer to the star, gaining energy from the interaction, but otherwise remains stable. For every planet it ejects, it settles more securely into its own orbit. So the giants survive. They stay. And the smaller worlds, the rocky planets, the ice worlds, the ones that might have harboured life, those are the ones cast into darkness. There's something almost cruel about it, isn't there? Ejected not by random chance or external forces, but by your own siblings. Cast out by the very world you formed alongside, in the same disk of gas and dust around the same young star. Family dynamics, writ large across the cosmos. Either the International Astronomical Union, the organisation responsible for naming celestial objects and defining astronomical terms, has a formal definition of a planet. You might remember the controversy when they used this definition to reclassify Pluto as a dwarf planet back in 2006. According to the IAU, a planet must meet 3 criteria. It must orbit the Sun, or more broadly a star. It must be massive enough that its own gravity pulls it into a roughly spherical shape, and it must have cleared its orbital neighbourhood of other debris. But notice the first criterion. It must orbit a star. By this definition, rogue planets aren't planets at all. They're something else. Planetary mass objects, perhaps. Sub-brown dwarfs, orphaned worlds. But not planets, technically speaking, because they don't orbit anything. And yet, this feels deeply unsatisfying. These are worlds with all the characteristics of planets. They have mass, gravity, possibly atmospheres and moons and geological activity. They may have formed exactly the same way as planets that orbit stars. The only difference is their trajectory, the fact that they're moving through space unbound rather than in a closed orbit. Is location really what defines a planet? Is the essence of planetness tied to orbital mechanics, or to the physical properties of the world itself? It's more than just semantic hair-splitting. These definitions shape how we think about the universe, how we categorize its contents, how we understand the relationships between different types of objects. And when the universe presents us with something that doesn't fit neatly into our categories, like a world that's planet-like in every way except that it doesn't orbit a star, we're forced to confront the limitations of our classification schemes. Maybe the universe is telling us something. Maybe our categories are too rigid, too tied to our own solar system's configuration. Maybe there's a spectrum of objects, from small rocky worlds to massive brown dwarfs, and rogue planets exist somewhere along that continuum, defying our attempts to draw clean lines. Maybe the cosmos doesn't organize itself according to human definitions. Maybe its content being ambiguous, letting things exist in the spaces between our categories, and maybe that's okay. Here's a speculative but fascinating idea. Rogue planets might be nature's way of spreading life between solar systems. Think about it. If a rogue planet has a subsurface ocean, kept liquid by internal heat, and if that ocean harbours life, then that planet becomes a kind of interstellar arc. A biosphere sealed beneath ice, travelling through space for millions or billions of years, eventually passing close enough to another star system to be captured, or at least to exchange material through some cosmic collision. It sounds like science fiction, but the pieces aren't impossible. We know that some microorganisms can survive in extreme conditions, frozen in ice for hundreds of thousands of years, or sealed in rock deep underground. If life exists in the subsurface oceans of rogue planets, it might persist for geological ages, yet protected from radiation by kilometers of ice, sustained by chemical energy from hydrothermal vents. And if that rogue planet eventually encounters another solar system, through capture, or collision with a moon or comet, or even a near miss that ejects material into space, it could, theoretically, seed that system with life. Microorganisms frozen in ice, delivered across light years of space, finding a new home on a new world. This idea is called panspermia, the hypothesis that life spreads between worlds, carried on comets, asteroids, or in this case, rogue planets. It's controversial, unproven, and difficult to test, but it's not impossible. Rogue planets might be more than just wanderers. They might be messengers, carriers of life's blueprint, spreading the possibility of biology across the galaxy in slow motion, one chance encounter at a time. Interstellar seed ships sailing through the cosmic dark for eons, waiting for the moment they might deliver their cargo to a world that's ready to receive it. A rogue planet passing near our solar system wouldn't necessarily be visible, not directly anyway, but it would leave fingerprints, subtle changes in the orbits of the outer planets, tiny perturbations in the trajectories of distant comets in the Oort cloud. Gravitational influences propagate across space invisibly, silently. Every massive object pulls on every other massive object, no matter how far apart they are. The force decreases with distance, following the inverse square law, but it never quite reaches zero. Even a rogue planet light years away exerts some infinitesimal pull on our solar system. If one passed closer, say, within a few light years, the effects would be more noticeable, not catastrophic, not system disrupting, but measurable. Neptune's orbit might shift slightly. Pluto's path might wobble. Objects in the outer solar system, those distant icy bodies beyond Neptune, might show unusual accelerations that don't quite match our models. And the fascinating thing is, we might already have this data. Our observations of the outer solar system are precise enough that anomalies would show up in the numbers. Unexplained deviations from predicted positions, orbital irregularities that don't match the gravitational influence of known objects. If a rogue planet passed through our neighborhood in the past few centuries, or even the past few millennia, the evidence might be sitting in our astronomical databases, waiting for someone to recognize it for what it is, a gravitational signature, the fingerprint of an invisible visitor. We'd be like detectives examining a crime scene, piecing together what happened from the evidence left behind. Except instead of fingerprints and DNA, we'd have orbital perturbations and gravitational anomalies, the universe's way of keeping records, the wanderer passed through long ago. But the memory of its passage remains, written in the orbits of worlds. On Earth, erosion is relentless. Wind and water wear down mountains, ice carves valleys, plate tectonics recycle the crust, burying old surfaces and bringing new material to the surface. The oldest rocks on Earth's surface are only about 4 billion years old, and those are rare. Most of the surface is far younger, constantly renewed by geological processes. But rogue planets don't experience this kind of erosion. There's no wind without an atmosphere driven by solar heating. There's no flowing water on the frozen surface. No rain, no rivers, no glaciers. At least not in the conventional sense, and that means their surfaces might preserve features from billions of years ago, almost unchanged. impact craters from the early days of planetary formation, when the solar system was still filled with debris, asteroids and comets crashing into newly formed worlds. Those craters might still be visible on a rogue planet's surface, perfectly preserved, frozen in time like fossils pressed into stone. If we could visit a rogue planet, we'd be looking at a museum of planetary history. Every crater tells the story of an ancient collision. Every geological feature speaks to processes that occurred when the planet was still orbiting its star before ejection. The surface is a record, unaltered by erosion, of everything that happened to that world across billions of years. It's similar to the Moon, in a way. The lunar surface preserves impact craters from billions of years ago because there's no atmosphere, no water, no weathering to erase them. But rogue planets might be even better preserved, because they're not subjected to the solar wind and radiation that slowly space weathers the Moon's surface. They're time capsules, archives of the ancient universe drifting through space, their surfaces carrying records of events that occurred when the galaxy was young. If we could learn to read those surfaces, we'd be reading the history of planetary formation itself. On Earth, we measure time through cycles. The rotation of the planet gives us day and night. The orbit around the Sun gives us seasons and years. The Moon's phases give us months. Time is structured, rhythmic, predictable. But on a rogue planet, these familiar markers as time don't exist. There's no day and night. The planet might still rotate, but there's no sun to create the contrast between light and darkness. Every moment is equally dark, equally night. The concept of daytime becomes meaningless. There are no seasons. Seasons are caused by the tilt of Earth's axis relative to the Sun, creating variations in solar heating throughout the year. But without a sun, there's no variation. No summer, no winter, just constant, unchanging cold. There are no years. A year is defined by one complete orbit around a star. But rogue planets don't orbit anything. They move in nearly straight line through the galaxy, influenced slightly by the gravitational pull of distant stars, but not bound to any of them. So how would you measure time on a rogue planet? Perhaps by geological processes, the slow cooling of the core, the gradual decay of radioactive elements, the occasional asteroid impact. But these occur on timescales of millions or billions of years. They're not cycles in any human sense of the word. Or perhaps time simply doesn't need to be measured. Perhaps on a rogue planet, the very concept of time as we understand it, time as something divided into units, structured into repeating patterns, simply dissolves. What remains is duration, pure duration. The slow, unbroken passage of existence without markers, without reference points. Just the persistent continuation of being, stretching backward into the distant past and forward into the unimaginable future, unmarked and unremarkable. Time exists, but it has lost its meaning. And in losing its meaning, perhaps it reveals something deeper, the way time actually is, beneath all our human attempts to divide it, measure it, contain it. The universe is approximately 13.8 billion years old. The first stars formed a few 100 million years after the Big Bang. And shortly after the first stars, the first planets began to form, which means the first rogue planets, the oldest wanderers in the galaxy, formed when the universe was still young. Perhaps as early as 13 billion years ago, when the Milky Way was just beginning to take shape, when the cosmos was a very different place. These ancient rogues have been drifting through space for almost the entire history of the universe. They formed when there were no planets like Earth, no sun-like stars yet. The elements that make up rocky planets, carbon, oxygen, silicon, iron, were less abundant back then, still being forged in the cores of early stars. So the oldest rogue planets might be very different from the planets we know. Perhaps they're more gaseous, less rocky. Perhaps they formed from the primordial hydrogen and helium that dominated the early universe. Perhaps they're strange alien worlds unlike anything in our solar system, and they've been travelling ever since, for 13 billion years, drifting through the galaxy as it evolved around them. They were there when the Milky Way collided with and absorbed smaller galaxies. They were there when the first supernovae enriched the interstellar medium with heavy elements. They were there when our Sun formed, 4.6 billion years ago. These ancient rogues were already 8 billion years into their journeys by then. They're older than almost everything we can see. Older than Earth, older than the solar system, older than most of the stars in the night sky. They're survivors from an earlier epoch of cosmic history, carrying forward through time like messages in bottles, sealed and unread, drifting through the ages. If we could find one of these ancient rogues, study its composition, analyze its structure, we'd be looking at a relic from the early universe, a world that remembers the galaxy's youth, that formed when the cosmos was still finding its shape. Wanderers older than time itself, in a sense, at least older than anything we've known. Most people associate auroras, the northern and southern lights, with Earth's interaction with the solar wind. Charged particles from the sun collide with Earth's magnetic field, are funneled toward the poles, and interact with the upper atmosphere, creating those shimmering curtains of green, red, and purple light. But rogue planets don't have solar wind. They're not bathed in the stream of charged particles that flows from a nearby star. And yet, some rogue planets might still have auroras. If a rogue planet has a strong magnetic field, generated by a liquid metal core perhaps, or by some other internal dynamo, that field would interact with the interstellar medium. The space between stars isn't perfectly empty. It contains wisps of gas, charged particles, the cosmic rays travelling at relativistic speeds. As a rogue planet moves through this tenuous medium at tens or hundreds of kilometers per second, its magnetic field would interact with these particles, channeling them toward the magnetic poles, just as Earth's field does. The result? Auroras. Faint curtains of light dancing in pitch-black skies, powered not by a sun but by the planet's motion through interstellar space. Auroras witnessed by no one on a world surrounded by darkness, glowing softly at the poles for billions of years. They'd be fainter than Earth's auroras. The interstellar medium is far less dense than the solar wind. But they'd be there, a subtle glow against the absolute black, created by the interaction of magnetic fields and the sparse matter drifting between the stars. It's a strange and beautiful image. A world in darkness, utterly alone, but still generating light. Not from any internal source, not from any nearby star, but from its own magnetic field interacting with the cosmic wind. Silent auroras on silent worlds, shimmering through the void. Here's an ironic thought. In a galaxy filled with hazards, supernova, gamma-ray bursts, stellar flares, asteroid impacts, rogue planets might be some of the safest places in the universe. Think about it. Planets orbiting stars are exposed to stellar radiation. Flares from their parent stars can strip away atmospheres, sterilize surfaces, disrupt magnetic fields. If the star goes supernova, everything within several light years is annihilated. Planets in the habitable zone, close enough to their stars to have liquid water, are especially vulnerable. They're bathed in ultraviolet radiation, X-rays, and stellar wind. Life on these worlds has to evolve defenses, ozone layers, magnetic fields, protective adaptations, just to survive the constant onslaught of energy from their sun. But rogue planets, they're not exposed to any of this. No stellar radiation, no flares, no risk of supernova. They drift through the quietest regions of the galaxy, the spaces between stars where hazards are rare and threats are distant. If a gamma ray burst occurs, one of the most energetic events in the universe, it won't touch a rogue planet in interstellar space. The radiation would pass through the region, but there's no nearby star to amplify the effects, no atmosphere exposed to the sky to be stripped away. If a supernova explodes, scattering heavy elements and deadly radiation across light years of space, the rogue planets in the region would be largely unaffected. They're small, dark, cold. The shockwave might jostle them slightly, but they'd survive. In a strange way, being alone, being unattached to any star, is a form of protection. Isolation becomes safety. The very thing that makes rogue planets seem lonely and desolate also makes them some of the most stable, protected environments in the galaxy. And if life exists on these worlds, in their subsurface oceans, sustained by internal heat, that life might be safer than life on Earth, protected by kilometers of ice, insulated from cosmic hazards, existing in a quiet darkness that never changes. The safest harbour in the galaxy might be a world without a sun. When we map the galaxy, we think in terms of stars, bright points of light scattered across space, clustered into spiral arms, and gathered into the dense core at the galactic centre. The Milky Way, from this perspective, is a luminous structure, a disk of starlight rotating slowly through the cosmic dark. But if we could map the rogue planets, if we could somehow see them all at once, lighting up every dark wanderer in the galaxy, we'd see something different. Not isolated points, but vast streams of worlds flowing through space. Because rogue planets don't move randomly, they were ejected from solar systems, which means they inherited the orbital motion of those systems, plus the velocity from their ejection. They move along trajectories determined by the galactic rotation, by the gravitational influence of nearby star clusters, by the ancient dynamics of the regions where they formed, and this creates structure. Yeah, rogue planets that were ejected from solar systems in the same region of the galaxy tend to move in similar directions. Over billions of years they spread out slightly, their paths diverging, but they still form coherent streams, rivers of dark worlds flowing through the galaxy's spiral arms. Astronomers have found similar structures with stars, stellar streams, groups of stars moving together, remnants of disrupted star clusters or dwarf galaxies that were torn apart by the Milky Way's gravity. These streams trace out the gravitational history of the galaxy, showing where ancient structures once existed. Rogue planet streams would be invisible, of course, but they'd be there, flowing through the spaces between stars, carrying billions of worlds along ancient trajectories set in motion eons ago. The galaxy isn't just a collection of isolated wanderers. It's threaded through with currents of darkness, rivers of rogue planets, invisible and uncharted, moving together through the cosmic night. Most rogue planets, after ejection, settle into orbits around the galactic centre. They're no longer bound to a star, but they're still bound to the galaxy itself. Caught in the collective gravitational pull of billions of stars, drifting through the Milky Way like dust motes suspended in air. but some rogues were ejected so violently that they're moving fast enough to escape even that. The escape velocity from the Milky Way, the speed needed to break free from the galaxy's gravitational pull entirely, is around 550 kilometers per second at our solar system's location. That's extraordinarily fast. Yeah, most rogue planets travel at tens to maybe 200 kilometers per second. But in rare cases, a planet can receive a gravitational kick powerful enough to accelerate it beyond escape velocity. Perhaps it was ejected during a close encounter with multiple giant planets simultaneously. Perhaps it was flung out during the chaotic disruption of a binary star system. Perhaps it passed near a black hole and received a gravity assist that sent it hurtling away at incredible speed. Whatever the cause, these ultra-fast rogues are no longer part of the Milky Way. They're intergalactic wanderers, travelling through the void between galaxies, destined to drift through emptiness far more profound than the spaces between stars. The nearest major galaxy to the Milky Way is Andromeda, about 2.5 million light-years away. At 550 kilometers per second, an optimistic speed for an escaping rogue, it would take roughly 1.4 billion years to cover that distance. And that's assuming a direct path, which is unlikely given the gravitational influences along the way. So these intergalactic rogues are embarking on journeys that dwarf even the already incomprehensible timescales of regular rogue planets. They're not just wandering between stars, they're wandering between galaxies, through voids millions of light-years across, through regions of space so empty that even dark matter is sparse. They're the ultimate outcasts, ejected not just from their solar systems, but from their home galaxy entirely, destined to drift through the cosmic web for billions upon billions of years, perhaps never encountering another galaxy, perhaps never coming close to another star. The loneliest of the lonely, wanderers in the truest, most absolute sense, somewhere within a few dozen light-years of Earth, close enough to be considered our cosmic neighbourhood, there's likely at least one rogue planet, possibly several. We haven't found it yet. Or rather, we might have detected it without realising what it is. Infrared sky surveys have catalogued millions of sources, objects emitting heat in the infrared spectrum. Most are stars, some are brown dwarfs, a few might be young, still warm rogue planets, glowing faintly in infrared wavelengths, but catalogued simply as unusual infrared source, or brown dwarf candidate. The data is there, sitting in astronomical databases, waiting for someone to look at it with fresh eyes, waiting for someone to notice that a particular object's spectrum doesn't quite match a brown dwarf's, and that its motion through space suggests a different origin, that it's too cold to be a failed star but too warm to be interstellar dust. And when someone finally recognizes it, when they realize they're looking at a rogue planet, not light-years or hundreds of light-years away, but right here in our neighbourhood, it will change our relationship with these objects entirely. Because proximity matters. A rogue planet dozens of light-years away is interesting theoretically, but it's still fundamentally distant, abstract. But one in our neighbourhood, close enough that we might someday send a probe to visit it, close enough to study in detail, to map its surface, to analyse its composition, that changes everything. It would be like discovering a new continent on Earth, except instead of land across the ocean, it's a world drifting through the darkness between our sun and the nearest stars, an invisible neighbour, silent and unseen, but there nonetheless, just waiting to be recognized for what it is. We've talked about how rogue planets might stay warm through radioactive decay, the slow release of heat from unstable isotopes in the planet's core. But there's another possible source of warmth: tidal heating. Tidal heating occurs when gravitational forces squeeze and flex an object. On Earth, the moon's gravity creates tides in the ocean, but it also creates tides in the solid Earth itself. The crust literally flexes up and down by centimeters as the moon passes overhead. This flexing generates heat through friction. The effect is more dramatic on moons orbiting giant planets. Europa, Jupiter's moon, is tidally heated by Jupiter's immense gravity. Enceladus, orbiting Saturn, is heated the same way. In both cases, the tidal flexing generates enough heat to maintain subsurface oceans beneath icy crusts. Now, imagine a rogue planet with a large moon, ejected together from their solar system, still gravitationally bound to each other. The planet and moon orbit their common centre of mass, and this orbital dance creates tidal forces. The moon flexes the planet flexes the moon. Heat is generated in both bodies. This heat could keep a rogue planet geologically active for billions of years. Volcanoes might erupt on the ocean floor of a subsurface sea. Tectonic plates might shift. Hydrothermal vents might spew mineral-rich water into the dark ocean, creating chemical energy gradients that could support life. All of this powered not by a star, not even primarily by radioactive decay, but by the gravitational embrace of a moon. Two worlds locked in an internal dance, generating warmth through their mutual attraction, creating habitable conditions in the absolute cold of interstellar space. It's a beautiful symbiosis. The planet keeps the moon keeps the planet warm. Together they wander the galaxy, a binary system of world and moon, isolated but not alone, cold but not lifeless. A partnership that transcends the need for sunlight. Here's a disorienting thought. On a rogue planet, there's no meaningful up or down in the cosmic sense. On Earth, down is toward the center of the planet, the direction gravity pulls. But we also think of up as toward the sky, toward space. And implicitly, we think of the sun as being up there somewhere, is even when it's on the other side of the planet. Our sense of cosmic orientation is tied to our solar system. The sun is at the center. The planets orbit in a disk, the ecliptic plane. There's an implicit orientation. The sun is up from below the solar system, down from above. But on a rogue planet, none of this exists. There's no parent star to provide a reference point, no orbital plane to define an orientation. The galaxy itself has structure. It's a disk with spiral arms. But from the surface of a rogue planet, that structure would be almost imperceptible. Just stars scattered across the sky in all directions. So which way is up? Toward the galactic center. But that's arbitrary. Toward the direction of travel. Also arbitrary. Perpendicular to the planet's rotation axis. That's at least physically meaningful. But it doesn't provide any cosmic orientation. In a sense, rogue planets exist in a state of true cosmic freefall. They're not bound to anything, not orbiting anything, just drifting through the galaxy's gravitational field, which at the scale of a single planet might as well be flat, uniform, unchanging. There's a kind of freedom in that, isn't there? No allegiance to any star, no obligation to maintain an orbit, no fixed point of reference in the cosmos, just existence. Pure and unoriented, moving through space without up or down, without beginning or destination. Absolute freedom. or absolute directionlessness. Perhaps they're the same thing. Not all rogue planets began as planets. Some of them, the smallest ones, comparable in size to Mercury or even smaller, might have started their existence as moons. Imagine a gas giant planet being ejected from its solar system through a violent gravitational encounter. The planet is flung outward at high speed, travelling too fast to remain bound to its star. And if the ejection is sudden and violent enough, some of the planet's moons might be stripped away in the process. The moon, now separated from its parent planet, becomes a rogue in its own right. But it's a rogue with a different history than a true planet. It formed in orbit around a gas giant, not in the protoplanetary disk around a star. Its composition might be different, more icy perhaps, rich in water and ammonia. Its internal structure might reflect its origin as a moon rather than a planet. These are the smallest rogues, the ones most difficult to detect. Because their mass is so low that their gravitational microlensing signal is tiny. They might be the most common type of rogue, or they might be rare. We simply don't know yet, because our detection methods aren't sensitive enough to find them reliably. But they're out there. Former moons, orphaned twice over, first when their parent planet was ejected, then when they themselves were torn away from that planet. They lost their sun and their world in a single catastrophic event. Now they wander alone, smaller and colder than most rogues, carrying with them the memory of a double exile. Once part of a system, once part of a planetary family, now just tiny frozen worlds drifting silently through the dark, so small that the galaxy barely notices their passage. The loneliest of all, not just worlds without stars, but moons without planets. These, if a rogue planet passed within a few light years of Earth, close enough to be considered a near encounter in cosmic terms, we'd have a window of opportunity. A brief moment, by astronomical standards, to study an object we might never see again. The planet would be moving at tens to hundreds of kilometers per second. At that speed, it would cross a distance of 1 light year in roughly 10,000 years. That sounds like a long time by human standards, but in astronomical terms, it's fleeting. We'd have perhaps a few decades, maybe a century, where the planet would be close enough for our best telescopes to detect it, study it, analyze its properties. We could measure its mass through gravitational effects on comets in the Oort cloud. We could attempt to detect its infrared signature if it's young enough to still be warm. We could track its trajectory, calculate where it came from and where it's going, and then it would be gone, receding back into the darkness, growing fainter and more difficult to detect with each passing year, until eventually it vanished below our detection threshold entirely. Not destroyed, not changed, just too distant to see. It would be like a visitor passing through, a cosmic traveller stopping briefly in our neighbourhood before continuing on its eternal journey. We'd have one chance to study it, to learn what we could, before it disappeared forever into the galaxy's vast spaces. And the strange thing is, this might have already happened. A rogue planet might have passed through our neighbourhood centuries ago, close enough to detect with modern telescopes, but too early in human history for us to notice. Or one might pass through in the future, 100 years from now, 1,000 years from now, when our technology is advanced to the point where we could send a probe to intercept it. Timing is everything. The universe doesn't wait for us to be ready. It simply unfolds, events occurring when they occur, regardless of whether we're watching. The discovery of rogue planets fundamentally changed our understanding of where planets can exist. For most of human history, we thought planets were defined by their relationship to stars. The word planet comes from the Greek word for wanderer, but the ancient Greeks were describing how planets wandered against the backdrop of fixed stars, not that they wandered through space unbound. Even as our understanding of the cosmos expanded, we maintained this star-centric view. Planets orbit stars. That's what they do. That's where they exist. The idea of a planet without a star was relegated to science fiction, interesting as a thought experiment, but not something that actually occurred in nature. But the universe, as always, proved more creative than our imaginations. Rogue planets showed us that solar systems aren't the only homes for worlds, that planets can exist in the spaces between stars, in regions we thought were empty, in environments we never thought to look. And this raises profound questions. If planets can exist without stars, what else might exist in ways we haven't imagined? What other configurations of matter and energy might be out there, waiting to be discovered, defying our expectations about how the universe is organized? It's a reminder of how much we don't know, namely how many assumptions we carry into our explorations of the cosmos. How often the universe surprises us by simply existing in ways we didn't anticipate. Rogue planets aren't just interesting objects, they're evidence of the universe's inventiveness. They're proof that nature doesn't confine itself to the patterns we expect, that there are always more possibilities than we've accounted for. The cosmos is stranger and more varied than we imagined, and rogue planets are just one example of that strangeness. One class of object we missed for centuries because we were looking only at the light, not at the darkness between. Some rogue planets have even stranger origin stories. They might have formed in binary or trinary star systems, systems with 2 or 3 stars orbiting each other, experiencing chaotic gravitational dynamics that make single star systems look peaceful by comparison. In a binary star system, planetary orbits are complicated. A planet might orbit both stars, travelling in a wide ellipse around the system's centre of mass, or it might orbit just one star, with the second star perturbing its orbit periodically. Either way, the gravitational environment is complex, unstable, prone to dramatic changes. Imagine a planet in such a system. In its sky, 2 suns, one perhaps orange, the other yellow, rising and setting in complicated patterns. Sometimes both suns are visible simultaneously. Sometimes one sets while the other rises. The interplay of light and shadow would be unlike anything in our solar system. But this complexity comes with a cost. The gravitational interactions between the stars and the planet can destabilize orbits over time. A planet that was stable for millions of years might suddenly find its orbit becoming more elliptical, more chaotic, drawn closer to one star and then flung away by the other. Eventually, it might be ejected entirely, thrown out of the system by the very stars it once orbited, and so it becomes a rogue, but a rogue with memories, if worlds could remember, of skies lit by 2 suns, of complex seasons driven by the orbital dance of binary stars, of light and shadow in patterns no single star planet ever experiences. Now it drifts in darkness, but once it knew a sky more complicated and beautiful than Earth's. Once, it had not one sun but 2 or 3, each contributing its own light to the world below. And then, in an instant of cosmic violence, it lost them all. Here's a paradoxical possibility. Some of the most Earth-like atmospheric conditions in the galaxy might exist on rogue planets. It sounds contradictory. How could a sunless world, frozen solid, drifting through interstellar space have conditions remotely similar to Earth? The answer lies in mass and internal heat. A very massive rogue planet, something with several times Earth's mass, could generate substantial internal heat through radioactive decay. This heat would rise through the mantle, warming the crust, potentially sustaining geological activity for billions of years. And geological activity means volcanism. Volcanoes release gases, water vapor, carbon dioxide, nitrogen, and sulfur compounds. Over time, these gases accumulate, forming an atmosphere. On a large enough rogue planet with enough internal heat, this volcanic outgassing could create and maintain a substantial atmosphere for eons. The atmosphere would be thick, insulating, trapping whatever heat escapes from the planet's interior. The surface temperature might rise above freezing in some regions, not from sunlight, but from the greenhouse effect trapping internal heat. And in the most extreme scenario, the atmosphere could even be breathable. Nitrogen and oxygen, released through geological processes, accumulating over billions of years into an atmosphere chemically similar to Earth's. You could, theoretically, stand on the surface of such a world and breathe. The air would be cold, far colder than anywhere on Earth, but it would be air. Oxygen, nitrogen, trace gases, a sky overhead, even if that sky never sees sunlight. It's one of the most counterintuitive ideas in planetary science. The assumption has always been that habitable conditions require a star, that you need sunlight to drive photosynthesis, to warm the atmosphere, to create the conditions for life. But rogue planets challenge that assumption. They suggest that habitability might not need a sun after all. Just the right mass, the right chemistry, and enough internal heat to keep the world alive from within. Paradoxically, some of the most Earth-like conditions in the galaxy might exist on worlds that never see the light of a star. On Earth, craters erode. Wind fills them with sand. Rain washes away their rims. Vegetation grows over them. Tectonic activity buries them or folds them into mountain ranges. Within a few million years, even large impact craters become difficult to recognize, their features softened and obscured by erosion. But on a rogue planet, craters last forever. Without wind, without rain, without flowing water or ice, there's nothing to erode them. Without tectonic activity, or with only minimal activity deep below the surface, there's nothing to bury them or deform them. They simply persist, unchanged, for billions of years. Every impact that occurred during the planet's formation, when it was still orbiting its star, still part of a young solar system filled with debris, those impacts left scars, and those scars remain, perfectly preserved, frozen in the surface like fossils in amber. If we could map the surface of an old rogue planet, we'd see the entire history of its early bombardment period. Every collision recorded. Every asteroid that struck during the chaotic first billion years of the solar system, leaving craters that have remained essentially unchanged for 4 or 5 billion years since. It would be like looking at a photograph of the early solar system. Not an artistic reconstruction, not a simulation, but an actual record, written in rock and ice, preserved by the absence of erosion, waiting to be read. Rogue planets are museums, archives of planetary history. Their surfaces tell stories spanning billions of years, stories that have been erased on active worlds like Earth, but remain legible on these cold, still wanderers. If we could visit one, if we could study its surface in detail, we'd be reading the history of planetary formation itself. a history preserved more completely on these sunless worlds than anywhere else in the galaxy. The irony is beautiful. The most pristine records of ancient solar systems exist on the worlds that were cast out of those systems. The outcast became the archivists. For decades, astronomers have searched for habitable planets by looking in the Goldilocks zone, the region around a star where temperatures are just right for liquid water to exist on a planet's surface. Not too hot, not too cold. The assumption has always been that life needs sunlight, or at least the warmth that sunlight provides. But the discovery of rogue planets, and the realization that some might harbour subsurface oceans, forces us to reconsider what habitable means. If life can exist in the lightless depths of a rogue planet's buried ocean, sustained by chemical energy from hydrothermal vents rather than solar energy, where then the number of potentially habitable worlds in the galaxy increases dramatically. We're no longer limited to counting planets in the habitable zones of stars. We have to include rogue planets with the right mass and composition, moons orbiting rogue planets, even smaller bodies that might maintain liquid water through tidal heating or radioactive decay. The habitable real estate of the galaxy might be vastly larger than we thought. Not just millions of worlds, but billions, possibly trillions. Most of them in darkness, most of them invisible to our telescopes, but habitable nonetheless. It's a profound shift in perspective. For so long, we've equated habitability with Earth-like conditions, sunny skies, surface oceans, photosynthesis. But the universe might be telling us that life is more versatile than we imagined. That it doesn't need sunlight, doesn't need a star, doesn't need any of the conditions we assumed were essential. It just needs liquid water, the right chemistry, and an energy source. And those can exist in the strangest places, beneath the ice of a moon, in the subsurface ocean of a rogue planet, in environments we're only beginning to recognize as potentially habitable. The question, are we alone in the universe, suddenly has a much larger search space, and most of that search space is dark, cold, and completely unexpected. The existence of rogue planets tells us something important about planetary formation. It's far more violent and chaotic than we once thought. For a long time, astronomers imagined planetary formation as a relatively orderly process. A star forms from a collapsing gas cloud. A disk of material orbits the young star. Planets coalesce from this disk, settling into stable orbits. The system matures, and those orbits remain stable for billions of years. But if up to half of all planets formed around stars eventually get ejected, as some models suggest, then the picture is very different. Planetary formation isn't orderly, it's chaotic, violent, destructive. For every planet that survives in a stable orbit, another might be cast out into the darkness. The solar systems we observe, like our own, aren't typical. They're the survivors, the stable configurations that emerge from an initial period of chaos and violence. We're looking at the winners, the systems that settled into equilibrium without ejecting all their planets. But for every stable solar system, there might be dozens of ejected worlds wandering the galaxy. The outcasts, the casualties of gravitational warfare that occurred billions of years ago. And this changes how we think about our own solar system's history. The current configuration of planets, Mercury through Neptune, orderly and stable, might have emerged from a much more chaotic early state. There might have been additional planets early in the solar system's history, worlds that formed alongside Earth and Mars and Jupiter, but were ejected during the violent reshuffling of the first few 100 million years. Somewhere in the galaxy there might be a rogue planet that once orbited our sun, a former sibling of Earth, cast out before our planet even fully formed, now wandering through the dark with no memory of its origin, no way to return. The solar system we know might be the remnant of something larger and more chaotic. And the missing pieces are out there, scattered across the galaxy, unidentifiable as our former kin. No two rogue planets follow the same path through the galaxy. Each one's trajectory is unique, determined by the specific circumstances of its ejection and the gravitational influences it encounters along the way. The direction of ejection depends on the angle and timing of the gravitational interaction that cast it out. The speed depends on how close it came to the giant planet that ejected it, and once it's travelling through interstellar space, every close passage near a star slightly alters its trajectory, bending its path, changing its velocity, sending it off in a slightly different direction. Over billions of years, these small perturbations add up. A rogue planet's path through the galaxy becomes a record of every gravitational influence it's experienced, every star it passed near, every cluster it drifted through. The trajectory encodes the planet's entire history in the galaxy, and because no two planets experience the exact same sequence of gravitational encounters, no two trajectories are identical. Each rogue planet follows a unique route through the Milky Way, a path that has never been travelled before and will never be travelled again. It's like fingerprints in a way. Each rogue planet carries a signature written in its motion, a history written in the curve of its path through space. If we could somehow track a rogue planet backward through time, following its trajectory in reverse, we might be able to determine where it came from, which star it once orbited, and when it was ejected, what gravitational interaction shaped its journey. But the farther back we look, the more uncertain the reconstruction becomes. Small errors compound, unknowns multiply. Eventually the trail goes cold, and we're left with a planet whose origin is lost to time, a wanderer with a unique story, but no way to tell where that story began. Here's a speculative but intriguing idea. In the distant future, if humanity, or any other civilization, develops the capability for interstellar travel, rogue planets might become essential waypoints. Interstellar distances are vast. The nearest star to our Sun is over 4 light-years away. At current spacecraft velocities, it would take tens of thousands of years to reach it. Even with significant advances in propulsion technology, interstellar journeys would still take decades or centuries. And during those journeys, travellers would need resources: water for drinking and fuel, minerals for repairs, perhaps even habitable environments for long-term stays. Rogue planets could provide all of this. A large rogue with a subsurface ocean would be a source of water. You'd need to drill through the ice, but the water would be there, protected from radiation, stable and abundant. The surface could be mined for minerals, metals, building materials, and if the rogue has a moon, tidal heating might create warm pockets beneath the ice, potential habitats where travellers could establish temporary bases, rest, resupply, and prepare for the next leg of their journey. In this vision of the future, rogue planets aren't desolate wastelands to be avoided. They're oases in the cosmic desert, stepping stones across the vast emptiness between stars, places where travellers can stop, replenish, and continue onward. The irony is delicious. These worlds that we think of as lonely, isolated, cast out, they might become meeting places, crossroads where different civilizations' paths intersect, ports in the interstellar dark. The loneliest worlds in the galaxy might someday become the most visited. Some rogue planets might be broadcasting, not intentionally, but as a consequence of their magnetic fields interacting with the environment around them. We know that planets with strong magnetic fields can generate radio emissions. Jupiter does this. Its powerful magnetic field interacts with charged particles in its magnetosphere, creating intense radio bursts that can be detected from Earth. A rogue planet with a similarly strong magnetic field would experience a different kind of interaction. Instead of a magnetosphere filled with particles from a stellar wind, it would interact with cosmic rays, high-energy particles travelling through interstellar space at nearly the speed of the light. When cosmic rays encounter the planet's magnetic field, they'd be deflected, accelerated, channeled toward the magnetic poles. And this process would generate radio emissions, faint signals in specific frequency bands, pulsing or varying as the planet rotates. These emissions would be incredibly faint. You'd need sensitive radio telescopes to detect them, and you'd need to know where to look. But they'd be there, a constant murmur from the darkness, generated by the interaction of magnetic fields and cosmic rays. We haven't systematically searched for these signals yet. Radio astronomy has mostly focused on stars, pulsars, galaxies, objects bright enough in radio wavelengths to stand out. But as our instruments become more sensitive, we might start detecting these whispers from rogue planets, faint radio signals from the void. Not messages, not intelligence, but the natural consequence of magnetic fields and high-energy particles. The sound of a planet singing to itself in the darkness, unaware that anyone might be listening. A reminder that even in silence, even in isolation, the universe is never truly quiet. One of the fundamental assumptions about life is that it requires stable conditions. A planet needs to maintain liquid water for billions of years, long enough for life to emerge, evolve, develop complexity. This assumption has guided our search for habitable worlds, leading us to focus on planets in stable orbits around long-lived stars. But rogue planets challenge this assumption in a profound way. A planet ejected from its solar system experiences one of the most catastrophic events imaginable. In a geological instant, perhaps just a few thousand years, it goes from receiving steady warmth from a nearby star to complete darkness and cold. Its surface freezes, its atmosphere might collapse. Any oceans exposed to space would turn to ice. If life existed on that planet before ejection, it would face an extinction-level event unlike anything we see in Earth's history. Not an asteroid impact, not a volcanic eruption, not even a nearby supernova, but the complete loss of the sun itself. And yet life might survive. And if organisms existed in subsurface environments, deep underground, in aquifers heated by geothermal energy, in caves insulated from the surface, they might persist through the catastrophe. The surface would die, certainly. But the deep biosphere could continue, sustained by internal heat, adapting to the new conditions over countless generations. And if life could survive the ejection itself, it could potentially persist for billions of years afterward. Subsurface microbial ecosystems, feeding on chemical energy from the planet's core, evolving in complete isolation from the rest of the universe. This raises an extraordinary possibility. Rogue planets might harbour not just life, but life that survived cosmic catastrophe. Life that endured the loss of its sun, and adapted to eternal darkness. Life that proves biology doesn't need stability. It just needs to be resilient enough to survive change, no matter how dramatic. If we ever find life on a rogue planet, it might be the toughest, most adaptable life in the galaxy. Survivors of an apocalypse carrying forward through the darkness, proving that life finds a way even when the universe seems to be saying it shouldn't. Most of what we know about rogue planets comes not from direct observation, but from statistical inference. We observe certain patterns, the frequency of micro-lensing events, the distribution of planetary masses in young star clusters, the dynamics of planetary formation simulations, and we work backward to estimate how many rogue planets must exist to produce those patterns. It's like being a detective examining evidence at a crime scene. You don't see the event happen, but you can infer what occurred from the traces left behind. When astronomers watch millions of stars and count how many showbrief brightening events, consistent with planetary mass objects passing in front, they can estimate the density of rogue planets in the galaxy. When they study the ejection rates in computer simulations of young solar systems, they can predict how many planets should have been cast out over the galaxy's history. And from these indirect measurements, a picture emerges: billions of rogue planets, perhaps more planets wandering between the stars than orbiting them. A hidden population, invisible to our telescopes but detectable through its gravitational fingerprints. But here's the unsettling part. Statistical inference has uncertainty. The error bars on these estimates are large. Maybe there are 10 billion rogue planets in the Milky Way. Maybe there are 1 trillion. Maybe there are 10 trillion. We genuinely don't know with precision, and we won't know, not with certainty, until we can detect them directly. Until missions like the Nancy Grace Roman Space Telescope give us a true census, counting individual rogues, mapping their distribution, confirming what the statistics suggest. Right now, rogue planets exist primarily as numbers in scientific papers, statistical shadows cast by events we can't directly observe. Real objects, certainly, but known to us mainly through mathematics and inference. The universe is full of things we know exist without being able to see them. Dark matter, black holes before we imaged one, and rogue planets, dark worlds whose existence we've deduced from the subtle ways they bend starlight and perturb the fabric of space. Mathematics revealing what telescopes cannot yet show. Some rogue planets might have rings, beautiful structures of ice and dust encircling the planet's equator, invisible in the darkness, existing for no eyes to see. Planetary rings form through various mechanisms, material from a shattered moon, captured by the planet's gravity. Dust and ice particles locked in resonant orbits, debris from asteroid impacts gradually spreading into a thin disk, and there's no reason rogue planets couldn't have rings. If a planet was ejected along with its moons, or if it captured material from the interstellar medium during its travels, that material could settle into orbital rings around the planet's equator. These rings would be completely dark, no sunlight to illuminate them, no reflection to make them visible. They'd exist purely as gravitational structures, particles orbiting in stable patterns, held in place by the planet's gravity and their own mutual interactions. But if you could somehow light them, if you could shine a flashlight on a rogue planet with rings, you'd see something extraordinary. Ice crystals glittering in the beam, dust particles scattering light, perhaps larger chunks of rock or ice, each following its own elliptical path, creating gaps and waves in the ring structure. It would be beautiful, majestic, a ring system encircling a world that no one will ever see, beautiful in perfect isolation. And maybe that's okay. Maybe not everything in the universe needs to be witnessed to have value. Maybe beauty can exist for its own sake without observers, without recognition. Ring systems around rogue planets, shimmering in the cosmic dark, no less real, no less elegant for being unseen. Every rogue planet is a lesson in planetary formation, a piece of evidence about how solar systems evolve, which configurations are stable, what kinds of gravitational interactions lead to ejection. When astronomers study rogue planets, measuring their masses, analysing their compositions, tracking their trajectories, they're not just cataloguing wanderers, they're learning about the violent, chaotic processes that shape solar systems. Why do some planets survive in stable orbits while others are ejected? What determines whether a young solar system retains all its planets or loses some to the galaxy? How do the number and arrangement of giant planets affect ejection rates? These questions can't be answered by studying stable solar systems alone. You need to look at what was lost, the planets that didn't make it, the worlds that were cast out during the formative chaos. Rogue planets are the fossil record of planetary formation's violent phase. Each one tells a story about instability, about gravitational dynamics pushed to extremes, about the narrow range of conditions that separate stable orbits from ejection. And by studying them, by understanding why and how they were ejected, we learn about our own solar system's history. We can model what might have happened in our own early days, whether there were additional planets that didn't survive, how Jupiter and Saturn's orbital evolution might have reshaped the inner solar system. No, the exiles teach us about the survivors. The outcasts reveal the history that the settled worlds have forgotten, and in a strange way that makes rogue planets essential to our understanding of planetary systems. Not peripheral objects to be catalogued and set aside, but central pieces of evidence about how the universe builds and destroys worlds. The story of planets cannot be told without including the ones that were lost. We don't know if rogue planets can support life. We don't know if their subsurface oceans, if they exist, harbour biology. We don't know if life could survive the catastrophe of ejection or emerge in the darkness afterward. But the fact that we don't know is itself profound. For centuries we thought we understood the boundaries of habitability. Life needs sunlight, we thought. Life needs a stable orbit around a star. Life needs conditions similar to Earth's, warm, bright, predictable. And then we discovered extremophils on Earth, microbes living in boiling water, in frozen Antarctic ice, in acidic hot springs, in rock kilometers underground. Life proved more versatile than we imagined. And then we discovered rogue planets, worlds existing in places we thought were barren, environments we assumed were lifeless. And suddenly, the boundaries of habitability expanded again. Maybe life needs a sun. Maybe it doesn't. Maybe it needs stable conditions over billions of years. Maybe it just needs to be resilient enough to survive change. Maybe habitability is defined by Earth-like conditions. Maybe Earth-like is just one possibility among many. Rogue planets force us to confront how much we don't know, how many assumptions we're making, how often we project our own experience, our own terrestrial biology, our own sun-bathed planet onto the rest of the universe. The truth is, we're still learning what's possible. Every new discovery, every strange exoplanet, every unexpected environment harbouring life on Earth, Every rogue planet wandering the galaxy expands the envelope of possibility, and that's what makes them so important. Not just as objects to study, but as reminders that the universe is creative in ways we haven't imagined yet, that there are still surprises waiting in the darkness, that our understanding is incomplete, evolving, always expanding. Rogue planets exist. We know that now. But what they mean, what they tell us about the universe's capacity to create homes for matter, for chemistry, perhaps even for life, that's a question we're only beginning to explore. The galaxy is full of wanderers, and each one is a question mark drifting through the cosmic night, waiting for us to discover what it might teach us. And so, we come to the end of our journey through the story of rogue planets. These wanderers in the darkness, these exiles from solar systems, these worlds that exist in places we never thought to look. There's something deeply humbling about rogue planets, isn't there? They remind us that the universe doesn't organize itself according to our expectations, that there are billions, perhaps trillions, of worlds out there in the spaces between stars, invisible and unknown, following their own unique paths through the galaxy. Some of them might be dead, frozen solid, geologically inert, but others might be alive in ways we're only beginning to imagine. Warm interiors beneath icy shells, subsurface oceans teeming with chemistry, perhaps even biology. Worlds that don't need suns to be habitable, that carry their own warmth through the darkness, and all of them, dead or alive, warm or frozen, are moving, travelling through the galaxy at speeds we can barely comprehend, yet so slowly that their journeys span billions of years, each one following a unique trajectory, influenced by ancient gravitational encounters, carrying forward through time like messages we don't yet know how to read. Maybe someday we'll visit one. Maybe we'll send a probe to intercept a rogue planet passing through our neighborhood, to touch down on that frozen surface, to drill through the ice and explore what lies beneath. Maybe we'll find evidence of life. Maybe we'll find only silence. But even the silence would teach us something. Even the absence of life would expand our understanding of what the universe contains. For now, they remain mostly invisible. Statistical predictions and occasional microlensing events, numbers in scientific papers, theoretical objects that we know exist, but can't quite see. But they're out there, right now, billions of them. Wandering through the darkness between the stars, each one a world complete unto itself, each one carrying a story written in rock and ice, and the slow mathematics of orbital mechanics. The galaxy is stranger and richer than we ever imagined, and rogue planets, these dark wanderers, these orphaned worlds, are proof of that strangeness, proof that the universe has more secrets than we've uncovered, more possibilities than we've explored, more stories than we've heard. Rest well, night traveller. And when you look up at the stars tomorrow night, remember, between those points of light, invisible and unnoticed, billions of worlds are drifting, dark planets on eternal journeys, each one a reminder that the cosmos is filled with wonders we're only beginning to understand. Sweet dreams,